Hello everyone, and welcome to the fourth webinar presented as part of Cisco CCNA V3, a short course facilitated by IT Masters on behalf of the Information Technology Professionals Association, or ITPA. My name is Guy Coward and I'll be your MC tonight, and your mentor is Matt Constable, who you'll hear from shortly. Before we begin, just a quick word on Zoom functionality and question asking. We ask that you direct all course content related questions to the Q&A section, and send all administration type questions to the support team in chat mode, or the chat box, I should say. You can choose to chat with panelists only, but I recommend changing your settings to include not only panelists, but all attendees, because often if you can start a discussion there, it's quite helpful as well. Maybe get an insight that we won't be able to get to in the delivering of the lecture. Often, we have people with great experience and great industry experience listening along, so they might be of use as well. Next week is week 5. This is week 4 of 5 of the webinars, and we'll finish the course content off, and also next week give you all of the information you need about the exam, the short course exam that is. So if you can hold your questions for now, that'd be great, and we'll get to those next week. But anyway, for now, can you please all welcome your mentor for tonight, Matt Constable.
Thank you, Guy. Thank you for your introduction, as ever. And welcome everyone to our fourth content week. So you'll probably all be pleased to know that this week is a little shorter on content. The last 2 weeks have been pretty heavy going in the switching topics and routing topics. And for good reason, because they make up a huge proportion of what is on the real Cisco CCNA exam. So we spend a lot of time there. So tonight is a little bit lighter. There is still some significant points that we need to cover off, and we will do so. But certainly we won't be heading into our too far into our second hour, all going well. So also means there's plenty of opportunity to ask questions as we go along. Now, before I get into the content for this week, I'll just point out a couple of things that I've made available today on the Moodle site. So first of all is the webinar slides for tonight. So they're there already, so you can have a look at those at your leisure, or you may already have downloaded them. The other thing I wanted to note was there was a couple of forum questions about rapid spanning tree. Now, rapid spanning tree is a quite detailed topic and probably deserving of a MOOC on its own. But what I have done is I've put up some additional readings under Module 2, LAN Switching Technologies. So this one here, Understanding Rapid Spanning Tree Protocol, and a little video vignette that's available on YouTube that I think are useful to assist your understanding with that particular protocol. And then there's a university study paper here comparing spanning tree to rapid spanning tree protocol, and just pointing out the differences in terms of the speeds in which ports chop and change their states, the different states, and configuration issues. So I definitely recommend you having a look at those when you get the time. Of course, this evening we are, if we scroll down, we're going to be talking about WAN Technologies and Infrastructure Services. So I'm going to switch that around a little bit though. I'm going to talk a little bit about NAT and DHCP in particular. They're the two main infrastructure type services that we need to cover off on for the real CCNA exam. And then we'll talk about WAN Technologies after that. I think the conversation flows a little bit better, particularly from where we came from last week. So we'll look at it that way. Okay, so we might as well kick it off. Hang on, what have we got here? So just got a lot new reading links for Module 2 are not working. Error comes up. Okay,
I'll have a look at that
guy.
I'll have a look at that one while you're delivering the content.
Yep. And Jeffrey,
yeah,
about the quiz question. To be honest, off the top of my head, I can't remember what the answers were, but I will have a look at that and we'll answer that before the end of the session. Before you leave tonight, I'll give you an answer on that. So I won't answer it just yet, but later on. Okay, so let's get started on tonight's topic. So first one we need to have a look at is NAT, or Network Address Translation. And really the whole reason, or the largest part of the reason for NAT becoming a thing, a technology, is this whole issue which we've discussed over, well, the first week and a little bit last week, with a shortage of IPv4 addresses. We know that IPv4 addresses are only 32 bits long, therefore there's slightly over 4 billion available IPv4 addresses, which I guess at the time IPv4 was written and released seemed like it was going to be enough forever, but we now know that of course that's not the case, with the way that the number of devices and the number of technologies that we now have connected to the internet, and the whole concepts of the Internet of Things, and moving forward into the future, we know that that many IP addresses simply isn't going to cut the mustard. So so NAT, IPv4 NAT, was initially designed as a method for taking those private IP addresses, which we've spoken about, so the ones mentioned in RFC 1918, so the 10 range, 192.168 range, and the 172.16 to 172.31 range. So those three ranges, as we know now, are only privately usable. You can only use them internally on your private networks. They're not routable out on the public internet. So NAT was developed as an adjunct technology to that, to allow those private IP addresses to be translated at the perimeter between the internal and external world, and therefore allow internal hosts to communicate with internet connected hosts by using a translated address rather than their own internal IP address. Thus allowing two things to happen. Firstly, saving of IP addresses, because enterprise world is now using private IP addressing, but also then allows them to still communicate with the external world, which they otherwise could not do because of the RFC 1918 standard. As we said, RFC 1918 private IP is not public addresses. You must use NAT to be able to get out onto the internet. There are many different ways and methods that you can get out from your WAN out onto the internet. We'll look at some of those shortly. But for the vast majority of cases, it results in NAT happening somewhere along the path until ultimately it must happen where the boundary between the internal and external world are. So the purpose of NAT is it says here, to translate between private and public IP addresses. But that's not technically correct, is it? Because it can translate between any address. It doesn't have to be private to public. It could be private to private. It could be public to public. It doesn't matter. It's just a method for translating from one address to another address as a packet flows through a router or through a firewall or other NAT-worthy device. And there are, the most common implementation of NAT is generally in that transference of, or the translation, sorry, of private IP to public when we're going out on the internet, but it is still a valid technology also to use internally, so to translate from one subnet to another subnet. Or it may, think of a case where you may have two networks that are now joining and they have the same private IP address range on each side, but because of the way the subnets are built, it's not going to match up, it's not going to work from a routing perspective. So you may actually use NAT in between them temporarily while you're translating everything over to the one base network range. So it can be used in that sort of circumstance as well, or certainly connecting extranet partners or remote access VPNs, lots and lots of different applications of NAT. But at the essence of it, it really is just translating one address to another. So it hides the specific private IP or specific IP source, or it can be source or destination. You can do source or destination NAT. Typically, we talk about source NAT, and CCNA certainly deals mainly with source NAT. So it hides the initial source IP address to an external or destination host. So all it sees is a NATed address, not the real address in turn. There has been some discussion in many different circles that I've been involved in about whether NAT is actually a valid security mechanism. And it can become quite a heated debate. My feeling is that it is a valid tool within a security toolbox. Some may argue that it's security by obscurity, and that's a fair point. My reasoning in including it in as a valid security tool is that it becomes part of the security architecture and infrastructure that you deploy. It on its own, certainly not a good security tool to use, not a good security protection, but as part of defense in depth strategy and using a lot of other technologies, and I think it certainly has its place as a security tool in addition to also being used for basic translation for routing purposes. But, you know, you guys will have your opinion on it, and that's fine, and you know, certainly generate some discussion on that either tonight in the chat or through the forums as well, because there's lots of different points of view on it, and there's, you know, there's the truth is intermingled somewhere amongst those different statements. With IPv6, NAT is not required, and again, this is not required at this stage because we now know that IPv6 addresses are massive, you know, 4 times as large as IPv4. So 128 bits in length. I'm not even going to take it, I can't even remember what the number is. I couldn't pronounce it anyway. It's a massive amount of IP addresses. But again, we thought that with IPv4 many years ago. So who knows what's going to happen in another 20 years down the track. They may develop another IP, might be IPv8, V10 by then, who knows? Or there may be an implementation of NAT at some stage in the future, but never know. So in terms of types of NAT, there are 3 main types that we will discuss with reference to the CCNA exam. So there is a static NAT, which is a simple one-to-one translation between 2 addresses. So a initial source address and then the corresponding address that it's NATed to on the way out. It can also be between a port on address to the same port on another address. So say for instance, an internal address, internal web server with an internal IP, port 80 on the way out, it might be translated to a different IP address, but the port number might stay exactly the same. So it can be between just 2 addresses, regardless of port. It can also be between 2 ports, 1 port on a single address. So either one of those can be considered static NAT. Dynamic NAT is where we use a pool of global addresses, so can be just a small pool, to dynamically translate traffic as it goes out past the device that's doing the NATing, whether that's a router or a switch or a firewall or whatever. And then we have our NAT overload or port address translation, which is pretty commonly used mainly at internet choke points. So translates the outbound traffic to unique ports from a single global IP address. So you might have lots of different private IP addresses internally that need to get out to the internet as they pass through the router. In this case, they would be NATed to a single IP address outbound. So it might be the external IP address on that particular router, or it could be another one, but it's an external IP address. And all of that traffic will go through coming from the single IP address. And it's differentiated by those ports, by the TCP or UDP ports. So some terminology that you need to get your head around for the exam, because this is really, really important to get your head around this. So we have an inside local, which this is a specific IP address that it's assigned to a host on the inside of the network. And I think, I'm not sure whether the next slide actually explains this in more detail, but I think I want to talk about this now before we get into this in any depth. We have this concept of inside and outside with respect to NAT, okay? And in most cases, inside refers to the internal private traffic, and outside refers to the external internet-based world, okay? So that's our general conception of inside and outside. But it doesn't have to be that. It can be inside might be VLAN 1, outside might be VLAN 2. So 2 internal networks, 2 internal subnets within the enterprise network. So it doesn't have to be this concept of internal network and internet. It's just one side and another. So inside is the network that you want to protect, and outside is what you're going to send your NATed traffic out to. It could, of course, be the other way around. So you could quite easily conceptually say that the internet is the inside and the internal network is the outside. It doesn't matter. It matters from a security perspective and a rules perspective, but from just getting a concept of what these terminologies mean, with respect to NAT, it doesn't matter which way you have them around. Inside is just a network you're natting. Outside is a network you're natting to. Okay, so it's important that you understand that. It's not always about enterprise and internet. So getting back to this. So inside local in that case is the specific IP address that is assigned directly to an inside host, to a host that you're trying to protect. So in normal sequence of events, that would be the private IP address of an internal host. The inside global address is the address that identifies that same inside host on the outside, to the outside world, or whatever the outside is, whether that's a DMZ, the internet, another subnet, whatever the case. So that's effectively the NAT address. The outside global is a specific IP address assigned to an outside host. So this is the destination if we're talking about outbound traffic from inside to outside. So this is the outside host wherever it may be. So in a typical case, this might be an IP address of a web server. The outside local address is an address that identifies an outside host on the inside. So that is the IP address that I'm going to get to go to the outside host. Now, in the vast majority of NAT implementations, the outside global and the outside local will be the same IP address. However, if you're using destination NATing, then they could be different. It's a different way of NATing. So instead of NATing the source address, which is what we normally do, source address outbound, we could also manipulate the address, the destination address as well, and NAT that as well if we wanted to. And you can do both at the same time if you want to. But that's sort of a bit more of a CCNP scope rather than CCNA to that level. So if we looked at a really quick example, and I'll turn my laser pointer on, although sometimes it doesn't effectively turn off, so I risk this. But anyway, we'll go down this track because it's easier for you guys to see. So if we consider this diagram here, on the left-hand side we have host A, which has the IP address of 10.1.1.10. We have a router A, which is NAT enabled. We have the internet. We have another router over here, which that should be actually router B. It's also NAT enabled. And on this router over here, we have a static NAT translation, which statically NATs the address 99.1.1.2 to the internal address of 192.168.1.5, which is host B over here. So if we consider traffic moving from host A in this direction to host B, in this case, host A's network is the inside, and anything on this side of router A is outside. So we're going to consider those. Now, router A is NAT enabled, and what we're basically saying here is it's using port address translation, so it's using overload NAT. So that means that any traffic that comes from the host A's network as it hits the router will be NATed. And in this case, we're overloading it to the external IP address on router A, which is 55.1.1.1. So if we consider our inside local, inside global, outside local, this is the way it fleshes out if we're considering host traffic going from A towards B. So the inside local address of host A is 10.1.1.10 because that is its statically assigned IP address. The inside global, if you remember, is the IP address of the inside host that the global network sees. So in this case, global is anything to the right of router A. So in this case, because we're doing NAT overload to 51.1.1.1, that becomes the inside global for host A. In terms of the inside and outside global and local, remember that the outside global and local refer to the destination host, the host we're getting to. Now in this case, we're going across the internet and we're trying to get to the IP address 99.1.1.2. So the outside global, or the outside host, as it appears to the global network, is 99 99.1.1.2, this translation here. The outside local is also the same because it's the address of the local host that is seen from the outside. So it's still 99.1.1.2, no different. It's exactly the same. Now, I haven't got them written here, but I want to work the example back the other way. So if we're considering from host B to host A, it works in exactly the same fashion. So host B, his inside local is 192.168.1.5. So that's the local address as seen from the inside. When we go to inside global, the inside address of host B as it's seen from the outside world is 99.1.1.1.2 because there's a static NAT translation in effect on this router here for that host. So that then becomes inside global. Now the outside global and outside local are still going to be exactly the same. They're both going to be the same IP address because they're from the perspective of host B. So if host B is talking to host A, then in both cases the outside global and local is going to be 55.1.1.1. And that's not going to be any different. Okay, so static NAT configuration. In order to configure NAT, as I said, we have this concept of inside and outside. So we need to tell the router which direction is inside, which direction is outside. So in this case, we're looking at Internet Fast Ethernet 0/0. So this is actually Cisco syntax, guys, for those of you that are not already aware. So interface FA 0/0, we give it the command IP NAT inside. So that tells the router that for NATing purposes, my fast Ethernet 0/0 interface is connected to what I consider to be the inside network. Following on from that, the ATM interface, which is normally, in this ATM 00 would normally be a DSL, some sort of DSL connection. I'm going to set that up as the outside interface. So now I'm considering, I'm talking about NATing from inside to outside, from my fast Ethernet network to my ATM or to my DSL connection on the way out. And in this case, with this example here, I'm going to map the public to private addresses. So IP NAT, and we'll talk a little bit about this more, but IP NAT inside source static 172.16.1.1 to 203.193.205.50. So what that statement is doing, it's setting up a single static NAT translation. So the IP, that's the protocol we're talking about, NAT, network address translation, inside, which means the addresses that we're expecting, that we're going to translate, is coming in from the inside interface. I'm doing source translation. So anything that comes from the source, 172.16.1.1, will be statically translated to 203.193.205.50 on the way out of the router. Now, as it does that, the router will dynamically do the translation. It will also have a static entry in its translation table, which builds that connection. And then traffic coming back into the router, when it hits 203.193.205.50, will then be unnatted back to 172.16.1.1. So it just sets up a static translation, one IP address to another IP address outbound. And then on the inside, when the traffic comes back in, it's simply untranslated or denatted and sent back to that private inside address. If we look at dynamic NAT configuration, a little bit more involved. So static NAT configuration, fairly simple. Inside, outside, static NAT statement, done. Piece of cake. But you've got to do that for every single address that you want to have a static translation for. Dynamic NAT translation, again, we identify inside and outside interfaces. So same as before, we inside, side, outside on the interface, depending on which interface. So like we did before, fast Ethernet 00, IP NAT inside, ATM 00, IP NAT outside. We then have to create a pool of global addresses, okay, because dynamic NAT configuration uses a pool. Now this pool can be as big or as small within bound as you like. So minimum of 2 addresses, but can be as big as you like. And the way we set that up is through this particular statement here. And these statements will be important to you for both your final exam for this particular MOOC, but also for the CCNA exam as well. You might not necessarily have to write these statements, but you will need to be able to recognize them. So again, if we go through the syntax, we have IP, protocol of choice, NAT, we're doing NAT to translation. Pool signifies we are going to use a pool of IP addresses. The pool name, so that can be anything. You can call it pool A, pool B, you can call it dog, cat, whatever you like, but you know, common sense would dictate that you do something that's meaningful. We then have a start and end IP address for that range. So in this case, we're using the pool of addresses between 203.193.193.1 and 203.193.193.50 with a net mask, with a 24-bit net mask. Okay, so that creates a pool, but that's all it does. We then need to identify which addresses to NAT using an ACL. So another use of ACL. So in this case, we're going to say access list 10 permit. So just a simple access list, that's all we need. 172.16.1.0/24. Remembering this is a wildcard mask, not a subnet mask. So what we're basically saying there is anything on the 172.16.1 network, we want to select that as being potentially NATed out through this pool of addresses here. Then the final step is we need to apply that ACL to the NAT pool. So what we're saying with this is IP NAT inside, so we're doing inside translation from inside to out. We're using source translation, so we're translating the source addresses as they're outbound. We're going to match them against list 10, which is access list 10. So anything that matches that access list will then be NATed using the pool that we created up here. So that now means 172.16.1.x, as it goes out through the router, will be mapped to one of these addresses here. Okay, now, a couple of different questions which I'm sure will arise. And one will be, I'm sure, once you run out of this pool, what then happens to any addition, because we've got 50 in the pool here and we've got potentially 254 addresses there. What happens when it runs out? Okay, so 2 answers to that question. Depends on iOS, can depend on platform. Answer 1 is that NAT will stop working. So once 50 addresses have been NATed, that's it, that's the limit, okay? Second answer is, and again, dependent on iOS, any remaining addresses, so this last address will be used as an overload. So the first 49 will be used as basically static one-to-one mappings. The last one will be used as an overload, okay? But it depends on iOS and it's not the same, okay? It's not as simple as saying that once it got to, say, 12.4 iOS, this is what they did. It's dependent on iOS and platform, okay? So it's not all routers are the same, not all iOS are the same. So it's one thing that's one of those things that you need to have access to a CCR account so that you can actually find that information out, because it's not always straightforward. Okay, so NAT overload configuration, last one we need to have a look at. Again, so in this case, we're sending all IP addresses out to a single, NATing them to a single IP address out. So we identify inside and outside interfaces, same as before. We identify the addresses we want to NAT using the ACL, same as before, okay, with this ACL here. We then apply the ACL to an overload, to our overload interface, which is this case ATM 0/0. So again, IP NAT, inside to outside translation using source address translation, match with access list 10. This time the pool, however, is interface ATM 0/0, and we're going to overload it. So that just says to the router, use the public IP address on ATM 00 and then use port address translation to distinguish between the different private IPs as they come through. Again, with all of these versions of NAT, they will all create quite a substantial network address translation table. which I might quickly in a minute, while you guys are putting out any more questions that you want to answer, I might actually get a router up and can show you some address translation for those of you that haven't seen it. Okay, so just some quick notes on troubleshooting NAT. So some basic commands that you can use: show IP NAT statistics, debug IP NAT. Be careful using that on heavily used NAT routers, unless you're going to also specify an access list on that. And why I say that is, if you've got an internet-facing router which has got a lot of translations on it, and you type in debug IP NAT, you'll overwhelm the router and it'll die. Because it's writing all those messages to the console, taking out processing, lots of bad things can happen. So the only time I would ever say that you would use that is either if it's on a very lightly used router, or if you also use it in conjunction with an access list. So you might, for instance, say, all right, let's have a look at a specific specific IP address that's outbound and see what that's actually doing. So say, for instance, you might have a single host that says, I can't get to the internet. I don't know what's going on. You would create an access list that might only just look at that particular host and apply that with debug IP NAT, and then you would be able to determine perhaps if there was a NAT issue with that specific host. But certainly don't use it for any more than just a handful of hosts at most. Any more than that, you could potentially bring your router to a grinding halt. And then there's show IP NAT translation to have a look at the status of the NAT table, so to see what translations are currently in effect. And clear IP NAT translation. That will clear all active translations out except for the static ones. So anything that's dynamic or overload will be cleared out and they'll have to rebuild. Static translations will be maintained, but their counters will be reset. Okay, so that's it for NAT. So I might, while we're looking, I'll get this router up so I can show you that, and we'll go through and answer a couple of questions that you might have on NAT.
Beauty. While you're getting that up, Matt, I'll just give you some notice for the first question I'll pop in. We've had a lot of lively chat debate about the figure on slide 5. People wondering why the number is 1.1 in host B, but it was 1.2 from host A. There's perhaps a bit of confusion about.
Okay, let's go back to that.
Slide.
That one there?
Yep.
Yeah, so sorry, what was the... Oh, okay, right, okay. Because, yeah, that's a really good question. Because this particular address, 99.1.1.1.1, is the IP address that's assigned to that specific router on its outside interface, okay? The 99.1.1.2, as it says here, it's a static NAT translation. So we're taking another address in that same subnet, 99.1.1.2, and we're statically, so manually setting up the translation through to this host. Whereas on this router over here, we're just using overload NAT. So in other words, anything on this side as it goes out will be translated to the external IP address on the actual physical router, whereas this one is using a different address. That's a good question. Nice pickup, guys. Okay, so let's have a look at this router here. So if, for example, okay, now we might just have to, I'm not sure how good that's going to be. So what we might do is, just bear with me for a second and I'll bump up the font.
Anecdotally, people say it looks okay.
Oh, okay. All right. Well, we'll go bigger.
But that's better.
Yeah, that's good. Okay. So as I was saying, so if we have a quick look at the, actually, let's just have a look at the translation table first. So if I go show IP NAT translations, now I hope that, now bear with me here because it's quite possible that I may actually write the wrong command in. And the reason I say that is because I'm used to writing all shorthand stuff, but I want to try and expand it out so it's easier for everyone to see. So show IP NAT translations, good, got it, bingo, first time. So what this is showing is the NAT translation table, which is currently sitting on my internet facing router. So the interesting, and this will go on for quite some time, I'm sure, because there's quite a few hosts on that. It will go on for quite some time. What you can see from this is what hopefully you can see from this is if I just scroll up a little bit and hopefully get back to there. Okay, so just around about here, I think is a good spot to look at. You can see in the first column, we talk about the protocol in use. So we've got TCP and UDP enabled. And that's why we use that IP static. That's why we use that IP keyword at the start of a NAT translation, because it enables translation for both UDP and TCP. What hopefully you can see then is that my inside global address. So this is the address that my inside hosts look like to the outside world. So it's 203.193.205.80, which just happens to be the static IP address that's allocated to my internet facing router. This is the port number that it's going out on. So the ephemeral port number that this particular connection is going out on. My inside local, so this is the actual IP address of my inside host, is this one here. Okay, so I'm using 10.10.30, so the RFC 1918.10 range, .151, so that's my host that I'm currently speaking through. The outside local, so this is the host I'm going to, this particular connection is going to. So we can see that's the public IP address of the particular host that this connection, that a connection is going to. Where that host is, I don't know. I don't know that IP address off the top of my head, so it could be anywhere. But needless to say, we see that's a protocol, so 443. We know that should know, hopefully, that TCP 443 is HTTPS. So it's some sort of encrypted web-based traffic. And we can also see that the outside global is also the same IP address, as I said before. So the outside local, outside global will generally be the same, will always be the same when we're using source address translation, which clearly I am. If we go down a little further, you'll see another entry here. So UDP translating to the same source address on port 23 outbound, and then this internal host, so that's a DMZ network of mine. So that's the inside local, so that's the inside address on port 123. So does anyone know what 123 is? Hopefully you'll know what that is. And then this is the external host that it's going to. So again, outside, local and global will be the same. Okay. And unfortunately, I don't have any statics on this one, so I can't actually show you a static. But what basically happens with a static is that there's a slight difference in the way that the actual it is displayed in the address table. But otherwise, it's exactly the same concept. So you have this inside global, inside local, outside global, always in that order. And you can see that there's a bucket load of translations there. Now, if I was to go, as I said before, if I go clear IP NAT translations, and I'll do this on purpose. Okay, it goes crooked me. I'll do that again. So incomplete command. So the difference with this command here is that you need to specify which translation you want to clear. So I could either clear a specific translation. So if I have a specific IP address that I want to stop, want to clear the translation, reset it. There are a number of different applications I'm sure some of you may have come across before that NAT will sometimes upset them. They'll stop working, and the only way to get them to work again is to clear the NAT translation. So you might clear it on a single host, or you could put a star like that and it clears the whole lot. In which case, if we go from quick enough, you'll now see the translation table is much smaller, but then as I start to issue the command again and again, you'll see that it'll slowly start to come back. So the connection table, so it's slowly starting to get bigger. So initially, so it doesn't break anything. It just means that that translation has to start again. Now, I'm not going to do debug IPNet on this one, because if I do that and the internet connection goes down, you'll lose me. And while some of you may think that would be funny and entertaining, we have to keep moving, so I'd better not do that. All right, so now let's just have a quick look at some questions. So the one about OSPF we'll look at later. Yeah, both routers are labeled router A. Yeah, I mentioned that. So the one on the right should actually be labeled router B, one on the left router A. Yes, router B. Yes, Theo, router B was doing one-to-one NAT static translation, correct? Yeah, Elias, so yes, outside local and outside global can be different, but they will only be different when you're doing destination translation, not source translation. So where you're doing source translation, they will always be the same. When you do destination translation, either with source address translation or differently, or by itself, then the outside global and local can be different. Absolutely, well, they will be different. A subnet, what would a subnet map look like? So I'm assuming you mean if I wanted to map an entire subnet. What that actually looks like is that there, or either one of those, either dynamic NAT or the overload is the same. So this here is mapping an entire subnet. So 172.16.1.0, that's mapping an entire subnet. And what I've been showing you here is effectively doing that. So that's what you'll see. You'll see all these different source addresses and ports. The issue, the point that becomes important with an overload then is the actual ports. They will be different for each of these hosts. It can't be the same. If they use the same ports, then there's a clash. Clearly that's not going to work. So that's how it distinguishes between the IP addresses in an overload or a dynamic situation where the pool has become full. Okay, security issue with having access to ILO from external, I believe. I'm not sure whether that's a question or a statement. There are some issues around security with ILO, but again, that's not something that you would use NAT to secure fully. There are other mechanisms in place with that as well. In terms of which NAT, there is no real advantage of one or the other. The answer is simply, it depends on what you're trying to achieve. So if you want to do a one-to-one NAT, then static NAT is the way to go. If you've got a small subnet internally that you just want to, you want a few to have few IP addresses outbound to have their own one-to-one relationship and others to just overload, then dynamic NAT is the way to go. If you've got lots of internal hosts and you don't care what address they appear at, but you just want to give them internet access, then NAT overload, like I'm doing, is the perfect way to do it. So it really, the answer to that question is it depends on what you're trying to achieve. So there's no real advantage one way or the other. CGNAT, that's a discussion for another time. So that's more of a CCNP one, but we can have an offline discussion. I can perhaps put some resources up about that if people are interested, but it's not specifically a CCNP thing.
And maybe start a forum discussion as well.
Yeah, absolutely. Absolutely. Yes, Simon, your question, and I'll only answer a few more because I'm mindful we want to get on, and I might have a look at the rest of them at the end. So I might answer two more. Does NAT command break the web session and application layer if it's dependent? Again, it depends. It depends on the application. If the application is programmed with sufficient a resiliency in it, then no, it shouldn't. There are certainly some applications that fail. There are some applications that will fail, yes. And there are also other applications that will fail, and then the only way to get them back again is to clear that translation. So it depends on the application, but it is possible that it will fail. So obviously, if you're in that situation, you've got an application that will fail. If that's the case, then you need to think about when you're going to schedule that clearing and what you have to do, what mechanisms you have to work around those problems in your particular environment. Is null natting more secure than denying traffic via ACL? No, not in my opinion, no. I think ACL is better rather than null natting or null routing. There's also some considerations about the order of processing through your router, which might impact some of your performance issues. But I would recommend probably it's better to do an ACL because you also have that logging component built into that, whereas it's more difficult to know what's really going on with null natting. And just actually one more because it's a quick and easy one. Yes, you can use multiple subnets for NAT, absolutely. NAT used for disaster, I'll answer this one too because there's only one left. NAT used for disaster recovery, like when a site is down, can you reroute the traffic to another? You can. It's not normally something you would use for disaster recovery though. You may, if you don't have sufficient disaster recovery built in, but I would think anyone that would require disaster recovery to a high level would be using other redundant mechanisms that would make the use of NAT irrelevant. But it's possible. Okay, I might just leave that connected for the time being. Okay, so back to this. All right. So NAT overload, we've already done that. Troubleshooting that, we've done that. Okay, DHCP server. So again, is it important? Oh, well, you know, it's important from the CCNA exam point of view to understand DHCP and how it works in terms of the routers offering DHCP addresses or how DHCP transits the router. But in real world, would you use it? Possibly. If you've got lots of satellite sites and you don't have a server at the satellite sites, you might have DHCP enabled on the router. Fine, if you know everything's remote at your central site. But usually, if you had a local server on site, you would usually run DHCP off the server. But you know, again, it depends on what you're trying to achieve. But certainly there to be used. Large networks, as we said, need DHCP servers. Really large networks normally would be running on some sort of Windows or Linux platform, so you wouldn't even be having this discussion about your router, I wouldn't think. DHCP is clearly the protocol of choice at the moment for distributing IP addresses automatically and giving them, leasing them out. Obviously works as IPv4 and IPv6 versions of DHCP. And there's a bit of a process that you need to go through. So there's DHCP Discover, where a host will come on and broadcast looking for a DHCP server. They then go through that offer and request process where the DHCP server will make an offer of an IP address to an end host, and that end host can either accept it by sending acknowledgement, or it can decline it and request something else. So, but there's that offer and request, or request and offer more correctly, request first and then an offer, and then an acknowledgement process. And once that's all gone through, then the host requesting a DHCP address will have access to its IP address, and away it goes. Just becomes part of the IP network and can start communication. To double up. Okay. Oh, that's it. Okay. So if that's all that's obviously not much on DHCP. So there's one other thing I want to mention about DHCP, and I don't think I am running DHCP on my, no, I'm not. Okay. So that's not, I'm not going to be able to give you a live demo of that. So in terms of DHCP setting up on a Cisco router, you can set up a pool of IP addresses. So not much different to what we did with our NAT. We set up a pool of addresses. We set up an access list that allows you to maintain control of that DHCP pool. We enable it on a particular interface facing in a certain direction, so not externally, hopefully, we face it internally. And then hosts, as they start to connect to that routed interface or through that routed interface, the DHCP request or broadcast will be intercepted by the router. It will check what subnet, so what VLAN basically, the hosts are coming from, and it will allocate a IP address appropriate to that particular subnet. So it works no differently to a DHCP server, like a Windows server or Linux server. One of the other main considerations about DHCP is that we know it works on a broadcast-based, using broadcast-based traffic, okay? And routers, of course, don't handball broadcasts, do they? We know they create broadcast domains, so they stop broadcasts. However, there's a process or a command, IP DHCP helper, where you can specify specific DHCP service for your network. So it might be on, say you've got a server VLAN, you've got your DHCP servers on that particular VLAN, you set up their IP addresses as helper addresses inside your Cisco router, and then any request for DHCP that hits that router will automatically be converted into a unicast packet and then sent to those servers. Okay, and then the router will handle the backwards and forwards of that traffic until such time as the end host gets a specific IP address and it's able to communicate on its own. So that's probably the main way many of us will use DHCP in a routed environment, is we'll actually set up IP helper addresses. And it really is just as simple as that. IP DHCP helper IP address, the router automatically then knows if it's got a valid, so first of all, it needs to have a valid route to that server. Once it's got that, then it will be able to convert any DHCP requests it gets into unicast, send it to that server, and then manage the communication between the server and the end host to get that IP connection up and running. So it's reasonably straightforward in terms of DHCP. Now, just a quick couple of questions. Will DHCP on a layer 3 switch router kill the server's DHCP service? No. I'm guessing, I think what you're talking about there is if you have the same subnets. If you have the same subnets enabled on your router and on your server, yes, it will cause an issue. Sorry, Guy, you're going to say something?
Yeah, Izzy's also asked a question, 2 questions up from there, wondering whether they're linked.
Okay, let me just have a look at that, sorry. Okay, yeah, how often is it used? I couldn't tell you, to be honest. I can only base it on my experience, obviously working with it. Very little. Mainly in small networks or mainly in sites that, satellite sites, so say WAN, smaller WAN offices that don't have access to a server themselves. So only very rarely. You will see it a lot in CCNP exams, and you'll see it a lot in the CCIE exam, but of course that's about implementing Cisco technology, so you would see it there. But in general, no, I wouldn't expect that you would see it all that often. In nowadays world, it's either going to be Linux based or Windows based. Auto config and Slack, that's based on IPv6, so we actually spoke about that in the IP6, so I might defer you to those particular resources rather than have a look at that again. So IP address, can you use a range with DHCP helper? You can use multiple IP addresses, but it's not a range. You have to use specific server IP addresses. So snooping is basically looking for, browsing or looking for DHCP type traffic. Okay, that's all it really is. So it's not necessarily related to the DHCP process. It's about snooping or looking for particular DHCP traffic and then doing something with it based on the configuration on your router. So whether that's forwarded on or block it or whatever the case may be. Windows Server is configuring DHCP on the router mandatory. With Windows Server is configuring. No, you never have it. DHCP on the router is never mandatory at all. And as I was saying before, you might not, if you have a DHCP server on your network, you're most likely going to use that to provide IP addresses for everything. You get yourself into trouble where you have DHCP server enabled on the router and on the server if they use the same subnets, then you'll definitely get clashes, you'll definitely get issues because they'll be answering requests at the same time. So you're going to get confusion happening there. You can certainly use one as a backup to the other. There's mechanisms for doing that. So you could have a server, for instance, and in the case that it's not working, you can use different technologies on Cisco routers to detect that and then enable the DHCP server on their end. You could even load balance between them, so have some subnets on one, some subnets on another. They're all possibilities. Would I do it? Probably not. If you've got a server, I think you're probably better off using that unless it's completely overwhelmed. DHCP server on a Cisco router, I think, has only got very specific small implementations that are useful. All right, thank you everyone. Right, so WAN basics. Okay, lots of stuff to potentially talk about in WAN, but not a whole lot that we need to really worry about for our CCNA. So we'll get through these slides reasonably quickly. So there's two popular definitions. So first of all, a WAN can be a network that spans a large geographical area, usually to interconnect multiple LANs. Okay, so that's a theory definition. So theory definition is it's a whole heap of connected sites together. A lot of local area networks connect together using this WAN. So that's a network. It could also be a network that traverses a public network or commercial carrier using one of several WAN technologies, which is more of the practical definition. So you can think MPLS, you can think ATM, frame relay, VPN, some sort of VPN. Even a VPN between two SOHO routers or SOHO modems is still technically a WAN because it's using a commercial carrier, the public internet. So they're two slightly different but similar definitions. So why do we use them? Because people in regional branch offices need to be able to communicate and share data with each other and with head office. If we don't have a WAN, we can't do that. Organisations often want to share information with other organisations that may be in a different country, and typically often are in a different country, certainly in different states, certainly in different towns. And to do that, we need some sort of WAN mechanism because point-to-point microwave and all those sorts of things, great technologies, but prohibitively expensive for large networks to own them themselves, so we go through carriers. Of course, we also have employees who travel from site to site to place, and often still need access to the company network while they're out on the road. So the road warriors, the remote access VPNs. So that technically, remote access VPN is technically a wide area network. So we're just using the underlying internet architecture to be able to get you to that particular connection. So some WAN characteristics: generally connect devices that are separated by broad geographical area, by a broader geographical area than a LAN can serve. So, you know, multiple kilometers or hundreds of kilometers, tens of kilometers. Yes, I know you can use wireless and microwave over short distances, and these are frequently used, but they're still technically considered to be a WAN technology rather than a local area network technology, which is typically constrained within a single site or building. WANs make use of services provided by carriers such as telcos, cable companies, satellite systems, and other network providers. And again, we'll look at those technologies in a second, what they actually are. WANs typically use serial-based connections of lots of different types that provides access to bandwidth based on a service level agreement or contract that you will sign with your service provider. And that can range from very small bandwidths, very small amount of bandwidth in the order of, you know, half a meg to a meg, sometimes 256K in some places, sometimes less, but not very often. But also other technologies that can scale up to hundreds of meg. So it can be very different. So WAN topologies, in terms of what a WAN looks like, there's 4 types that you basically need to get your head around for CCNA. So there's point-to-point, which is reasonably straightforward and easy to understand. I think I've got a diagram in the next couple of slides which will help, so we'll just go through these ones. Hub and spoke, where you've got a central site which has multiple branches, it looks like a bit like a spider, I guess. Goes out to the satellite sites. We have a full mesh where every site can connect to every other site. most expensive, most redundant obviously, but certainly most expensive to build. And then we've got single versus dual homed. So if we look at a physical topology here, so that's a physical topology of a LAN, obviously, just to compare it to what we're going to have a look at in a minute. So we've got a number of classrooms, a number of offices, all connected by switches and hubs, but basically it's a one small little network. So that's physically what it looks like with the physical devices located in switching cabinets, and we've got our cables going out to each place, each host and each building around a place. And some of those could be fiber, some of them could be copper, but one or the other. If we look at the logical topology of how that looks, this is what we're looking at here. So it looks a little bit like the physical topology, but less cluttered, and just shows us the way that traffic is routed and the way traffic works from a logical perspective. So a little bit more information with respect to the IP addresses on this and the subnets, but otherwise very similar. If we look at the WAN topologies and how they look very different. So in a point-to-point, so there's usually a lot less connections, with the exception of the mesh topology, a lot less connections and a very different look to it. So point-to-point topology is basically just that, two routers separated by vast distances, connected by some sort of WAN technology. Could be ISDN, could be DSL, could be frame, could be ATM, might be MPLS, but probably unlikely if there's only two hosts. Hub and spoke, this is where we've generally got a central office in the middle here, and then we've got multiple spokes, each one going off to another site. So all of these WAN links terminate at the head office, and then they branch out to each of the branch offices as they go. But the topology basically, physical topology basically looks the same as that as well. In a full mesh topology, which is something that MPLS basically uses, and there are other technologies that have used it in the past, but certainly MPLS is the easiest one to implement it with in many ways. We have all our different sites, and every site connects to every other site, which is absolutely fantastic from a redundancy point of view. Because you know, if any one link goes down, or even sometimes two links, or if all links bar one goes down at a particular site, it still has a way to get to every other site. However, obviously it's more expensive because you've got to have, in this case, 5 links at every single site. So huge expense, great redundancy, huge expense. Is it worthwhile? In a traditional sense, if you're using individual services for each of those links, absolutely not. Particularly now, absolutely not. Although there are some places that use them that have very high requirements for redundancy, and things like data centers will also use them to a degree, but not generally as complex as that. In an MPLS environment, basically what happens is the internal, if you think of there being a cloud in here, the MPLS environment is made up internally in that cloud of a lot of different switches and routers owned by a service provider, and they run that MPLS cloud over the top of that, so that when you get your individual services from each site coming into that, they can automatically connect to all the other services in a mesh structure, but with only the need for one service out to each site. So it's sort of a mesh structure, but it's almost a combination between hub and spoke and mesh. So it's almost the two combined. So there's a mesh with full mesh within the cloud, which as a customer you don't see. The cloud just looks like the hub, and then you've got the spokes going out to your branch network. But inside that particular hub is a full mesh. That's almost a combination of the two. So if we look at the physical side of things from a point to point, that's it. Pretty simple, pretty straightforward, limited to 2 nodes. Anything more than that, and it no longer is a point to point, it becomes something else. Logical point to point, this is what it really looks like from a provider point of view. So if at this stage we're assuming that these are serial links, and we're going to assume they're frame relay or ATM, it doesn't matter what they are really, but these networks connect into a provider cloud, and then inside that provider cloud there could be a lot of other hardware sitting in there that we don't see because that's provided by the provider. We don't care, we don't worry about that. all we see is a direct point-to-point connection. So from our point of view, if we're looking at the source router over here or the destination router, it appears as if they are directly connected to each other. Of course they're not, there's lots of different traffic in here, but they appear as if they're connected point to point. The appearance is a little different depending on the technology. So if we look at frame relay, for instance, we will see some evidence of the provider connection, the provider end. If we're using ATM, similarly. If we're using MPLS, no, we won't. All we see is this point-to-point connection. We don't see the internal hosts at all. So some basic WAN terminology that you will need to use, and I apologize, this is American terminology, but that's what you're going to need to know. And we can turn that into a little bit into the Australian terminology as we go along. So we have a network provider. So this could be Telstra, it could be Optus, it could be Bendigo Community Telco, it could be iiNet, doesn't matter who it is. And they have a thing called a CO, which is basically a central office, what the Americans call a central office. We then have a local loop. So the local loop is the cabling between the service provider and the demarcation point, which is generally the CSU-DSU. So CSU-DSU is an American term. The Australian term is NTU. Okay, so where you see CSU-DSU, that means NTU. So network terminating unit. So the demarc point for the vast majority of providers is that NTU. So they'll provide cabling and everything into your office up to the end, and they'll provide you with a network terminating unit, which is basically their fancy little modem. And then from your side in, that's your responsibility. From that NT unit back into the provider network, that's their unit. That's their responsibility. So the demarc point is where that changeover of responsibility occurs. So in this case, the American are saying, well, the demarc point is somewhere in the middle between the cabling and the CSU-DSU. In Australia, it's generally at this point here, the NTU unit is generally the demarc point. The CPE stands for Customer Premises Equipment. That can be provided by your provider. I used to work for a provider, and in our case, our demarc was actually this point here, because we would provide the NTU, well, Telstra or whoever or Optus or whoever the carrier was, would provide the NTU. We would then provide our own program router for the customer. That CPE would be our responsibility. So the demarc point would actually live here. So it actually, in effect, there's actually two demarc points. One was here, and that was between us as a provider and whoever provided the carrier service, so Telstra, Optus, whatever. And then we had this demarc point here, which was a demarcation between us and the customer. And then we've got our corporate network over here, which just connects in to the customer premise equipment to get them access to the service provider network. So WAN connection types, what have we got? So we got three types that we need to talk about. We've got dedicated, which is synchronous serial, which just means the bits are all synchronized, but sent serially. Okay, so typically used point to point. We have asynchronous serial. So an example of that would be ISDN. In which case we've got, so the telephone company or service provider, we have multiple hosts, whether that's a desktop sitting at someone's home with a ISDN NTU, could be another site, another branch site over here, and they all connect in using ISDN in this case, or it could be DSL, for example, into the telephone company to provide what is called a circuit switched network. Basically means packets are switched by circuit. So a circuit is built between, say, this particular device here and this router, and while that circuit is up, all packets are sent via that circuit, switched via that circuit. We then also have a synchronous serial, which uses packet switched. And although it appears very similar to this one up here, in that there's a single connection from each way, disappears into a cloud. Now inside that cloud, there are a number of different routers, or potentially a number of, well, they usually are, quite a number of different routers. And depending on the routing protocols or different issues or events that may be happening inside that provider network, the path that packets take to get from here to here may be different. from time to time. So therefore it's a packet switched technology. So the switching or the way in which the packets are sent may be different on a packet by packet basis depending on algorithms or transitional conditions inside the network. Whereas with circuit switching, that's not the case. Circuit switching, once a circuit is built and dedicated, packets will always traverse that same circuit. Packet switching, not necessarily the case. There could be multiple ways in which it could go. Could be multiple equal load balancing, in which case the packets may be switched a different circuit on a packet by packet basis. They may not be too, but they could be. The potential is there for that to happen. So technologies, some of the technologies. So there's VPN technologies, which we know about. Okay, so we've got our IPsec VPN, we've got our GRE tunnels, if you want to loosely classify it as a VPN. And we've got our SSL VPNs as well, as three typical examples that you might use. So again, using a carriage network or a publicly available network, the internet, to create WAN circuits, WAN network. We then have MPLS. So MPLS is basically provided by a provider in a cloud format. So it's just a whole mesh of switches and routers inside their core with MPLS set up on it. So it's analogous almost to VLAN tagging. So if you think of VLANs in the LAN world, MPLS is very similar in a WAN implementation. And you don't worry about this. You don't need to know too much about this for a CCNA level. You don't have to know the ins and outs of MPLS, but it basically tags packets based on whichever WAN they belong to. So which customer they belong to. So it's very similar to VLAN tagging, just at the WAN level. But it's provided as a cloud. So as a customer, you don't really see what's inside that cloud. You just see a connection. And if, for instance, you had a network with 10 Cisco routers in it, all communicating over an MPLS VPN WAN, all you are actually going to see is those routers. They're going to appear like they're all directly connected to each other. You're not going to see the MPLS environment at all. In most cases, it can be set up so you can, but in most cases, it'll be secured in such a way that you can't actually see that. So Metro Ethernet is basically providing Ethernet services in a metropolitan network. So actually in that case, you probably maybe think more MAN. MAN is, so Metropolitan Area Network is probably becoming more of a discussion around that now. Broadband point-to-point over Ethernet. So again, another Ethernet-based service, but using broadband. So broadband is really just a catch-all term for a lot of different technologies, but basically PPP over Ethernet, so dial-up over Ethernet, if you like. And then we've got our two traditional WAN technologies, our frame relay and our ATM. You won't see too much of ATM on the CCNA exam. Maybe the odd question just about the theory of it, but not too much in there at all. You might see a little bit on frame relay. So make sure that you have a look at the packet tracer labs around this area, because that'll give you some good background on the actual syntax that you're going to need to come across for the exam. So if we quickly look at IPsec VPN, look, I'm sure we're all very familiar with this. But basically this is how it looks. Clearly we have a few different examples of the different ways in which you can connect via a VPN. So you can have a perimeter router and a firewall sitting behind it at your main site. Now, VPNs can easily terminate on a router. In this case, we're terminating on the ASA, which is behind the router, but it could equally terminate on the router as well with an appropriate IPsec feature set. In this case here, we've got a business partner which has their own Cisco router. So the VPN tunnel is built from that router to the ASA at the main site. We have a regional office which has got an ASA sitting there. So that's an ASA to ASA tunnel. And we have some guys sitting at home, the small office, home office router, which also creates a site-to-site VPN coming into the ASA. We then have a mobile worker with, in this case, a Cisco AnyConnect. So basically a piece of software that pretends it's a VPN device and allows him to connect over any service provider or internet-based service into the ASA to give him a VPN connection like he was actually there in the office. The keys to get out of this is we have two main types of VPN, IPsec VPN. We have a site-to-site, So site to site, big office to big office, or small office to big office. And then we have a remote access VPN. The main difference is that the site to site VPNs are not transportable. Okay, they're nailed up for specific sites, specific locations. A remote access means you could be anywhere in the world effectively. If you've got an internet connection, you can get back to your office. So GRE, people often think of GRE as a VPN type protocol, and it is. The difference really between GRE and IPsec is GRE does not have any encryption. So it doesn't give you confidentiality in any way, shape or form. But it does allow you to set up a tunnel across an IP network. So the good thing about GRE is that you can carry multiple protocols over GRE if you want to do that. So it's a bit of a throwback to ancient times when we had IPX, AppleTalk, other sort of protocols that Cisco supported. You could build a GRE tunnel across an IP-based network, like the internet, for example, and you could tunnel your IPX and your AppleTalk and whatever else over that if you wanted to do that. Still used nowadays. There are implementations I've seen of using it, mainly with ATM, and when I say ATM, I mean automatic teller machine. So bank ATM networks, where GRE was used to tunnel ATM-specific traffic across a WAN. But that was a private WAN. That wasn't certainly going over the internet. You wouldn't want that traffic going over the internet, obviously. But over a private LAN, we used GRE tunnels in that particular bank that I work for. But now that's gone sort of by the wayside. Now in that particular organisation, there's now a whole complete dedicated network just to the ATMs, which I think most banks do now, rather than running a GRE tunnel over your corporate WAN leading out to the ATMs. So a little bit of a throwback to a bygone era GRE. So MPLS, stands for multi-protocol label switching. Been around for several years, as we've said. Similar to frame relay and ATM conceptually in the way that it provides services. And as I said before, it forwards packets by attaching labels or adding a label to it. So instead of, you think of VLANs, we think of VLAN tagging. So as traffic goes across a trunk, if we remember back to our discussion on VLANs, as it goes across the trunk, we add a VLAN tag to it so that it knows what VLAN that traffic belongs to when it gets to the other end of the trunk. MPLS is similar in that as packets come out of a WAN site into the MPLS cloud, that MPLS cloud will tag it with an MPLS identifier, allowing the network to determine what network it's actually a member of. There are two ways in which MPLS is often provided. So there's a layer 2 MPLS VPN. This is where the customer controls the routing. So the service provider only provides connectivity from a layer 2 perspective. So that then is more analogous to VLANs than what layer 3 MPLS is. So layer 2 MPLS VPN, very similar to VLAN in many ways. And you as a customer will control the routing over that layer 2 VPN connection. Typically provided in circumstances where applications need layer 2, need that control over layer 3 in order to be able to work. A layer 3 MPLS VPN just takes it a step above. So now the service provider routers control the routing, and the layer 3 services are sent across the service provider backbone. So it's just the next abstraction up. Just takes that routing away from you as a customer. Some customers like that, some customers hate it. Depending on how big you are as a customer and what your in-house tech is like, you may actually decide that you want to, just a layer 2 is enough for you. Okay. Pricing, similar. Obviously layer 3 is a little bit more involved for the service provider. So it's going to be a little bit more expensive, but it depends on your provider, it depends on your agreements, all that sort of stuff. So, but there's certainly things that you need to consider when implementing this, but not necessarily for the exam. Benefits of MPLS, use of one unified network. Okay, so you provided a core MPLS structure by your service provider. It's one unified, fault-tolerant, high-speed network. There's better IP over ATM integration. So the technology facilitates better integration of IP over ATM. You can run a BGP-free core. So in this case, you don't have to have the service provider, if they're providing the routing internally in that core, they might use BGP. In fact, most of the service providers do, because they also have internet involved and lots of other things involved. But if you're running an MPLS VPN, you can run OSPF or EIGRP or RIP or whatever you like over the top of that, particularly if it's layer 2. You can run whatever you like over the top of that. Doesn't matter. That's up to you. So you don't have to worry about then having to implement BGP and having that expertise of BGP. It's a point-to-point model for MPLS VPN in many cases, because, as I said before, the actual intricacies of the inside MPLS cloud are hidden from the end user. Typically, you don't see that. All you see is point-to-point connections to your other sites. Optimal traffic flow. You've got, and basically what we're saying there is we've got bucket loads of bandwidth in the core, in that MPLS cloud provided by your service provider, and it gives you optimal routing capabilities, because if you run your own protocol over the top, it settles it all down. You can pick and choose where you want things to go. And obviously there's that high-speed network that the service provider provides that gives you that extra bandwidth, depending on obviously your service level agreement, the contract that you that you're provided with them. It also allows you to do some basic traffic engineering as well. That's not to say that it's as heavy duty as QoS, full quality of service, but it does allow you to do some components of traffic engineering at that layer 2 level. So Metro Ethernet, as I said before, metropolitan area network, think of it more as a MAN based on Ethernet technologies, really, really high speed links. So we could potentially be talking terabyte speed links. Again, layer 2 level technology, and it's really more about the cable that you use. So either copper or fiber typically. It's more typically fiber in most places. You'll be provided Metro Ethernet via fiber. But again, it's the same sort of process as, say, a frame relay or an ATM. You'll get a termination point provided to you by the service provider, and you'll connect to that via whatever technology you agree. It could be a fiber converter. It could be fiber directly into a switchblade. It could be copper, handoff, whatever the case may be. But the Metro Ethernet is really more about the connecting media and the bandwidth that you're paying for. It's really just a local area network on steroids. So others, as we said, broadband PPPoE, PPPoE ATM. So we're talking about what we typically use in, if we talk about dial-up, so ADSL is a form of PPP over ATM. ADSL is a form of ATM. If you look at the guts of ADSL, what underlines it, it's underpinned by ATM. Frame relay, again, very common. Many of you will have seen frame relay and had experience with that. Very common, and something that you will have to fiddle around a bit with in the exam. And that's why I'm saying there's buckets of packet shaper labs to have a look at around this, around frame relay, and I fully encourage you to have a good hard look at those. I haven't been able to show you anything because obviously I don't have a frame relay connection, unfortunately. I wish I did, but I don't have a frame relay connection at my disposal. Otherwise, I'd spend a little bit more time looking at that, but we haven't got it, unfortunately. So, and then ATM, if you think of ATM as being very similar to DSL, if you're familiar with DSL connections, there's not a whole lot of difference in the underlying architecture between that and ATM. But again, not too much of that you will be required on the CCNA exam. And that, so I told you we wouldn't go for the full 2 hours. We're done for this week. So next week we're going to look at infrastructure security. So bits and next week the content, all the content looks at infrastructure security, infrastructure management, and we'll drill down on some of those content in our hour to hour and a half next week. So questions. Now I see there are a few, so let's have a look at them now. VPLS and Metro Ethernet can be provided by Metro Ethernet, yes, but it can also be provided in other ways as well. So that's a bit of a depends question, but it can be. Okay, WAN connection types. How does this translate between DSL, coax cable, SHDSL, fiber to the, yeah, okay. So they're all related, but ADSL, for example, is the underlying, is the layer 2 technology. Coax cable, you're talking about a layer 1 technology. SHDSL and fiber are, they're basically different levels, so levels of the OSI model. So what you're talking about there is a mix between layer 2 and layer 3. They're all WAN technologies, they're all WAN connection types, but they don't often, you wouldn't normally use all of those, well, you don't use any of those at the same time, but they're different technologies for providing a different type of WAN connection based on the speed you require, the services available in your area, what your provider can provide, and obviously how much you're willing to pay. What MTU would MTU be those Telstra buildings in regional towns? MTU. No, no, NTU.
Yeah, might be NT. Yeah, that
Yeah,
can't.
NTU. Now, NTU, I was going to say MTU is a very different thing. NTU is just a terminating device. So it's basically, they're basically like little modems. So if you think about a small office, home office DSL modem, that's often what they look like, and they are often provided by Telstra, but also by Optus and other places as well. And they are generally located in the regional offices, yeah. So that's what you'd have at your remote WAN site. Okay, that one we need to ask. Will CCNA expect people to set up VPN to connect via WAN to a local network in the network? No. No, they won't expect that. That's more of a CCNP level. Where does SD-WAN fit in the WAN topologies? That's a good question, and actually I'll answer that by saying I've got a really good resource that I'll put up for you that will probably answer that in better detail than I can in the time we've got here, and I'll probably be clearer than me too. So I'll put up, to answer your question, Dame, I'll put up a resource for you, well, for everyone, not just for you, obviously, to talk a little bit more about that.
On resources, Matt, I had a look at the.
Oh yes, yeah, yep.
Yeah, if you could just send me the links for the two extra external resources you sent. There was an error with those, okay, and I'll chuck them in.
All right, no worries. All right, thank you. Okay, does an MPLS WAN service require config and or hardware at the ISP or purely? No. It basically, yeah, so MPLS is basically, the MPLS side of it is all configured by your ISP carrier. So there's nothing that you have to do. If you buy an MPLS service from a provider, there's nothing you have to do on an MPLS side at all. You will basically be provided with a point to connect to, and as far as you're concerned, it's just a routed point. So you don't have to know anything about MPLS at all to buy an MPLS WAN. If, however, you're developing your own in-house MPLS WAN, then yes, you would need to configure specific MPLS technology across your MPLS core. And that's definitely not a discussion for CCNA. Would it be appropriate to say that the internet uses a full mesh topology as a number of... No, I wouldn't say, no, I would say that the internet is a collection of full mesh networks, but connected via hub and spoke. So it's a mix. It's definitely not a full mesh. It may appear like that from a home user point of view, but it's definitely not a full mesh. There are certainly components of it that are full mesh, but it's a mixture of lots of different topologies. So there's no simple answer to that one either, but a really good question. We only have Metro Ethernet, 100 meg in our office, 10 gig in the data center. Haven't seen Family 5-10 years. Is it still very common? It is. There is still a bit of it around. Certainly not as common as what it was, as you said, 5 or 10 years ago. It's more, and certainly since the advent of MPLS, it's probably died off even more. But it is still used by some large government organisations, that would probably surprise you. But there are certainly some Victorian state government departments that still use frame relay, and that's built around contracts and all sorts of weird things. But in terms of, if you were to go out and buy a new network, would you buy a frame relay? No, no. They're much better technologies to use now, so you certainly wouldn't use it. But you can tell by the way that Cisco even talk about it still in their CCNA level exams. It's still a foundational topic in a lot of ways, that it's you will still see it, but certainly not as much as what you used to. So no, good question. Okay, so that's it. There's just that other question revolving around the question. So I'll just have a quick look at that question. So if you've got any more questions, just pop them through and I'll just have a quick look at this and get that question answered for Jeff.
While he's doing that, I'll just pop on and say apologies. There may be some of you, and perhaps quite a few of you, who are caught out by the Australian Eastern Daylight Savings Time move. Over the last weekend.
Yes, I wondered why there were so many came on a bit later.
Okay. I didn't explicitly state it in the weekly email, so I'm terribly sorry for that. I did change the UTC time, but I should have made it more explicit, and I'm sorry for that.
Okay, answer to that question posed is OSPF is indeed the most trustworthy. So the question, and I'll just rip out some of the other questions just in case someone hasn't seen them.
Beauty, and I'll add to my little spiel earlier. Yes, so for those of you that were caught out, we'll have the recording up for you tomorrow, and you can catch up then.
Okay, so that's the question there. Which of the following routing protocols is the most trustworthy? So it is OSPF. So the trustworthy part refers to the administrative distance, which we were talking about last week. So if you remember, administrative distance is a measure of the trustworthiness of that routing protocol or routes learnt by that routing protocol. So it's only used between routing protocols. So if you're in a situation where you're using more than one routing protocol on your router, so say for instance OSPF and EIGRP, then the administrative distance will determine which one of those routing protocols is seen as the most trustworthy. If you're only using a single protocol, so say just OSPF, administrative distance is meaningless. And you know what? That is actually wrong, because the answer in this was actually B, but we'll send us the answer is actually C. It's actually EIGRP. So there you go. That's a very good question, because thinking back off my head, knowing the EIGRP has an administrative distance of 90, OSPF is 110. So the answer is actually EIGRP. So I apologise profusely for that. It's not OSPF. The answer is actually C, EIGRP. So thank you for raising that question, whoever that was. I can't remember who it was. Jeffrey, thank you. Yes, the answer is actually C, EIGRP. So thanks for that. Thank you for clarifying that. Well, I'll pop up a little thing on the forum about that, or Guy, if you want to.
Yeah, I'll have a chat with James, the IT Masters Overlord, about what we're going to do about that one. For those that have already taken the test, you can of course take it again, but we might just make sure. Yeah, no,
we'll make that publicly known, because that's it. That's important. Yeah, yep.
Yeah.
So apologies for that, guys.
We might even just make that quiz not a hurdle requirement for taking the exam. We'll
yes, or work out what we're going to do. So yeah, apologies for that. You are that's good that you raised that question, Jeffrey. Thank you, because it's definitely the answer is C, EIGRP. All right, so we've got a couple other quick questions. Does the DHCP relay function work in MPLS VPN network? Yes, because MPLS basically gives you that point-to-point situation. So yes, it will. You can forward DHCP relay functions over that, over MPLS VPN. So yep, that's no worries to do that. Quaz in the next meeting, there might be, off the top of my head, I can't remember, but there may be a little bit of Quaz in there. If it's something that people are interested enough in, there's not a lot of it in the CCNA exam, but if that's something that everyone is interested in, I can put in a few slides on that to go over the basic the basics of QoS, absolutely. Because I don't think next week again is similar to this week, so we haven't got the really long session that we've had the last couple of weeks. So I can have a look at that. So thank you for that question. Virtual practices. Yeah, so I assume by that you mean me actually sitting here with a router, doing stuff. It would be nice to do a little bit more of that. The practical labs, the packet tracer labs are provided to give you your hands-on. I'm often reticent to go through the actual packet tracer labs because I'd rather people work through them on their own. They get better learning experiences that way. And unfortunately with the routers that I have at my disposal now, having got rid of a huge proportion of my lab, I don't have that facility to provide that hands-on demo at any one stage, unfortunately. But where the opportunity arises, we certainly can. So it hasn't arisen until this evening. So, but thanks for that comment. I'll definitely take that on board for future classes. So thank you. So Guy, that looks like that's wrapped up the questions. Anything else you want to say?
Just enjoying the banter between those who engage in daylight savings time and those who do not.
Yeah, there's always that bit of rivalry there.
Other than that, yes, we'll get those links to you with the further external resources, and yeah, we'll confirm what we're going to do about the quiz question. So yeah, thanks very much for your generosity with the time in terms of questions, Matt, again, and delivery. And thanks for everyone for hanging around for another webinar. Next week we'll again cover Matt's topics and also have a brief chat about the exam. So no one's caught short. The short course exam, I should specify, given we're talking about CCNA.
Exactly.
But thanks very much, Matt. Yeah.
All right, no worries. Thank you, everyone. Talk to you next week. Bye.